Now let's welcome our second speaker, Dr. Tomas Pevny. I think he's already here, and let me give a brief introduction about him. So, Dr. Tomas Pevny received his PhD degree in computer science from the State University of New York, Binghamton. He's currently working in the Artificial Intelligence Center, Czech Technical University in Prague. His research interests include applications of non-parametric statistics, such as machine learning and density modeling, with a focus on computer security, steganography, and steganalysis. So today, the title of the presentation will be explaining hierarchical multi-instance data, let's welcome Dr. Pevny for his presentation.
Yeah, thank you very much for the introduction. So as Andrew said, I am probably mostly practitioner, but let's say the problems that I try to solve in practice are, I try to solve them, let's say, with, grain of theory. So I'm not satisfied if it just works. I want to know why. And I'm going to talk about the type of data that I deal a lot, and we decided to call them hierarchical multi-instance data. So let me motivate you first. What type of data it is? So 2 years ago, Abbas, one of my employees, has hosted a challenge on Kaggle, and there are plenty of challenges on Kaggle. This one was, from my point of view, a little bit special. So the task in that challenge was relatively easy. You got a scan of your home network with full of devices, and you were supposed to identify the class of the device. So there were sending classes, so that's pretty similar. But the interesting part of the data, because the data didn't have a tabular form, which most of us are used to, and let's say that most papers in machine learning assumes that your data comes in a form of a tensor, but the data were stored in the JSON. And JSON is essentially a hierarchical format. It consists of a node, and each node can have other nodes as a child. And engineers really love this file format. So probably everyone heard about JSONs, everyone heard about HTML or XML, but there are dozens of others. For example, protobuffer is the same type, or message pack. And if you go to history, I think that this type of file format was invented somewhere in the 60s by IBM. And the first, let's say, file format I know about was called General Markup Language. And if the markup rings a bell with HTML, it was essentially a predecessor. So apparently, engineers and people really likes to put their knowledge into these structural formats. And I think it makes a lot of sense because it allows you to very naturally goes from, when you are describing an object, to go from a high level to a, let's say, very fine level. So when I talk about this to my colleagues or friends, I typically use an example of an iris dataset by Ronald Fisher. He describes a plant by 4 features, and those features are measurements from a blossom. But in practice, there is more features on the plant. So it can have a lot of leaves, and it can have a lot of blossoms. But describing a leaf is quite complicated. So you start to give finer details. Okay. So by the way, if anyone has any questions, just interrupt me, and I will try to answer. And I hope that you see the screen. Okay, so let's go back to my motivational example. So this is an example of one sample. We can see that it has like a bunch of classical features. We can call them like fixed tensor stuff. That's like these strings. But there are arrays that those arrays can have different number of items. So that's something we have to deal with it. And those arrays do not have to contain only strings, but they can essentially contain another like JSON. So it's a type of recursive format. And if I show you quite some examples from this data set, you should clearly get the challenge. So that one sample can be very small and the keys can be missing. So we have to deal with like missing keys. If I show you the next two examples, you can see that if there are arrays, like this services contains an array of items, that's something like an open port. You can see that one example has 2 items, the other example has 4 items, and the third example is missing completely this key and things like that. And then you can get something like this. This is still the sample from the same data set. It's just huge. It's one of the biggest. And ideally, you would like some kind of a unified way how to process your data. Something ideally like convolutional neural networks. So, what's our...
Thomas,
yeah.
for us who are not programming, can you
okay, yeah.
the old folks, can you sort of conceptualize the challenge?
Okay. So imagine that your sample has a tree structure. Okay, and tree structure. And that would be something like a schema of those samples. And in some samples, like portion of this tree can be missing. Okay, so imagine that you will get a sample, and on the first level, one sample will have 7 leaves, and in the other, or let's say 7 nodes, and it is in the other sample, he will have just 3 nodes. Okay, so there is this variability. Then, some nodes can be missing, so the nodes are of different types. So, for example, here, if I go from top, there is a node which we will call services, and that node in the first sample contains 2 subnodes, like part and protocol, and it contains, like on the same level, it has like other 4 types of nodes. It's device ID, IP, MAC, and this MDNS services.
So, I think let me just rephrase because we have like a biomedical data set, for example.
Okay.
So let's say the patient sometimes misses some visits, right? Or they haven't have all their blood exams or some other exams that everybody else has, right? So these are the sort of the missing parts, right?
So that would be something like that. So imagine that you can have like series of, let's say, blood samples or these blood checks. Yeah. And in each set or in each check, they could test for different types of, like measurements in your blood. And that measurements, for example, doesn't have to be a simple scalar, but that measurement can be, a little bit more complicated. You can have more values. And the measurements can be of different type. So there is a lot of heterogeneity in the data.
Right. And also missing data. That's what you said, right?
Yeah, exactly.
Missing leaves,
So that's what you can see between, for example, this 1 and 2. This sample number 1, he's missing this MDNS _ services. Right? So the missing stuff is definitely there. So this type of data are actually super common in like engineering practice, and you can see that in your example from like medical, you can very naturally use them to describe your medical type of data, or at least I believe that, but I didn't have access to medical data, at least of this type.
Yeah, so thank you very much. Thank you. Yeah.
Yeah. So yeah, sure. Welcome. Like, thank you very much. Okay. So I said, like, what's our option? And this is like option that I have gathered through papers, what people are doing. And maybe you as a theoretician consider some approaches crazy, but nevertheless, people are writing scientific papers about it. So the first thing is the feature engineering. It's like gold standard and it works. So when I showed you that Kaggle competition, the guy who won it, I examined his solution, and it was essentially a feature engineering with some like small neural network, whatever. Right. And when I talk to like diehard practitioners in Avast, well, they are like, yeah, we do features and the JSON is not a problem. Like for them, like they are really good in designing features, or let's say the command. Well, the second, what is surprising that people are really doing that, they would take the JSON or, for example, like, you know, binary program and just make it into an image, you know, just doing like zigzag scan or go row by rows and throw on that some like huge convolutional neural networks. And that sort of makes sense because if you think how much research has been put into the vision, you know, you can get surprisingly good results. Like, even though that to me the approach sounds crazy. But the other approach is that people would ditch the structure and they would treat the JSON as a text, right? And they would use some huge language models that we use nowadays, and they would hope for the best. It's gonna probably work. I was trying that, but I am really not an NLP person, so I kind of failed. But the neural network has to learn the abstractions or the structure that you have in the data by itself. Well, and the fourth approach that I will try to sell you is this hierarchical multi-instance learning. So, you know, just for amusement, like I took the data set and I created images from that. So I took the JSON and, you know, I make it into the figures. So each row of these figures shows like one type of devices, and you can see that, well, they are a little bit similar. So the CNN was able to catch some pattern. Okay, well, text look a little bit more crazy. You would essentially need to learn the structure, but you would need to deal with big samples, but definitely doable. I don't think that, but it's not subject of this talk. Okay. And so the fourth approach that I'm selling, as I said, is the hierarchical multi-instance learning. And our solution is surprisingly simple. So we knew that the file format has a tree structure. And at, let's say, each node can have quite a complicated you know, subtrees remaining, but we can adopt a following, I would call it invariant, that for the given node can expect that each of its children can be represented by a vector. So the only role, or let's say the part of the model that is going to be modeling each node knows that its input is going to be vectors or set of vectors, and he will output a vector. And this is a design invariant that we keep, and it allows us to, let's say, process this type of data. And it's really simple. You go from leaves. So leaves are typically numbers that machine learning, or let's say the type of entities or tokens that the machine learning deals with for ages. Like numbers, well, we can treat it as a number, right? That's super simple. We just make it a scalar. Okay. Well, if there is a variable which have a very, let's say, low number of possible values. So, for example, network protocol, you typically use TCP, UDP, maybe ICMP, and that's it. Then we are very good. We typically represent it as a one hot encoded value. So it would have like vector of dimension 2. And then we typically have something like strings, and there is plethora of ways how to deal with strings. In our library, in our tooling, we use n-grams. but I am not saying that you have to use n-grams. You can use whatever you wish, which takes a string as an input and produces a vector of a fixed value. Okay, so that's trivial. So what else do we have in JSON? So we have key value pairs. So you can see that the services contains a lot of items, and each item is a key value pair. So there is a port and protocol, let's say always like with it. And that's again like super simple. We know that the port is essentially an identifier of a token, and we can do Cartesian products. Right? So we take a representation of a port, we take a representation of a protocol, and we just lay them side by side, and that's it. Problem solved. Okay, so that's easy. And the tricky part is services. Like the services is an array, and that array can have arbitrary number of items, including zeros. And we need to take an array with which, by our design, we know we can represent it or abstract it as a set of vectors. And we need to produce a single, we have to produce a single vector of a fixed dimension. Well, the solution is quite easy and obvious. You either take element-wise mean or element-wise maximum, or maybe some more complicated function like let's say norm. But this allows you to reduce this variable number of items or in the array into a single vector. So we are maintaining our design contract, and you keep repeating these steps. So we have another array. I again convert it into the array of a fixed dimension. Then we have the topmost dictionary, which we again concatenate, and then we end up with a single vector describing, let's say, the whole sample, and we can do the prediction. And where are the neural networks? The neural networks are at each arrow. So I have left them aside, but each arrow is a feed-forward neural network. And notice the subscriptors. So if I'm processing port, or let's say feature describing the port, I always use the neural network F1, right? Because I am let's say projecting an entity. I know the input dimension, and that entity is going to be optimized for the port. I have the protocol, and I always, for a protocol, use function F2, like feed-forward neural network. When I concatenate them, I use F3 and so on. Sorry, right? So this whole scheme contains a bunch of neural networks. It's you can optimizing end to end. So just by using labels on the output of the function F9, I can take a gradient all the way through to this function in the leaves. So the f theta has some parameters, and I can take a gradient of the output with respect to the parameters of this F1, which allows me to use essentially like all the machinery that was, that we are playing with last 15 years. Essentially, stochastic gradient descent, and it's optimizable, like end to end. And that's the power, I think. So we did some comparison. On the end, I will show you how we have some library that does that quite efficiently. We call that library MIL. It comes with some default values. If I use them on the 3 dataset, mutagenesis is like dataset from the ages. The device ID is the device ID from the Kaggle competition I told you about. And the Ember is a dataset for detecting malware. So that's quite big. You can see that with so each value is an accuracy. So ideally we would like to have 1.0. We are far. We are a little bit far from that. This is when we use our library as is like by default. Very naive. You can see that the results are relatively good. If we tune it, by playing like the number of layers, neurons, and should I use dropout, should I not use dropout, like I call it, I think it's relatively boring, but we can spend ages with that. You can beat the competing approaches. So we look into the prior art, like what's the best people have achieved on these data sets. So for example, this number is the winner of the Kaggle competition. So we beat it like a little bit and so on. So that was, let's say, the practical motivation. Any questions? You are stunned.
Thomas, someone says there's no dynamics here, right? Things are not changing, right? These are all static, right?
Okay. So the scheme is mostly static, but the numbers, so I would call it this way. So the master scheme has to be static, right? But there can be, as I said, like some samples can be missing parts, right? And if there is an array, the array can have different numbers of items. Right? So you can have a sample which this array with services will have the length 0, and then you will have another sample which will have this array containing like 100 items. But generally, we assume that the schema is more or less static. Yeah, like we allow for some like dynamicity.
Yeah.
But
Also, the state of the art that you're comparing, is it what's the best second best after use? It's a graph-based method. What is it?
Okay. So this is excellent question. So actually, no. Like as I said, like that guy who won the Kaggle competition, he was doing features. This Ember either used some type of neural networks, but definitely not graphs. I think some type of neural networks and mutagenesis, I don't know. We look at we found a web page who is showing like who is best on mutagenesis, and like we look there. Okay, so someone mentioned graphs. So that's, I think, an excellent point. And it's also like a great intro to my transition to my second part of the talk. So in general, graphs, there are a few differences. In graph neural networks, you typically assume that the vertices are either all the same, or the number of types of the vertices is very low. So you assume that there can be like low number of types of vertices, right? So if I would be talking about like a computer network, there would be client, there would be server, but let's say the number of types of vertices would be low. Here it is quite the other way around. So we have very high number of vertices. There is an interesting, let's say, relation between this hierarchical multi-instance learning data and general graphs. So what I deal with is essentially a tree, or let's say directed acyclic graphs. And you know that for this type of graphs, you can do an exact inference, and you can do it essentially in a single pass. So if we are going back to, let's say, the probabilistic, let's say, graphical models, you know that if there are no cycles, you can do inference very quickly in a single pass. Whereas if you have a general graph with cycles, we typically resort to belief propagation. And I think that with belief propagation, at least what I read in Bishop, you don't have any theoretical guarantees. Like you will get something, but I don't think that you have theoretical guarantees about correctness. Okay. So the fact that we are not dealing with general graphs essentially buys us, efficiency, because we do the inference in a single pass. We go from the leaves to the root, and we have the final value, whereas in graph neural networks, you will typically do message passing.
Thank you.
Okay, awesome. So then let's right now with the boring part, and that's the theory. So as I say, I'm mainly like practitioner, or I consider myself a practitioner. But when I came up with this scheme, I was starting to think if that scheme is correct. In neural networks, by correctness, I mean, can I approximate, arbitrarily closely any continuous / measurable function? Because when I entered my university, it was high school. So on university, I learned about something which was called, concept of dense functions, or let's say the concept of set of dense sets. And there is something similar in neural networks. So that goes back to, I think, 91 and 93. And Leshno in 93 proved something which is called universal approximation theorem on Euclidean spaces. So we knew that if, let's say, our sample is represented in Euclidean space, which I assume here, and there is a function that I want to approximate, and that function is, let's say, continuous, or in his work, he goes a little bit farther and he then generalizes to measurable functions. You know that, his theorem, which I printed here, it's quite awful, tells you that you can combine it, or you can arbitrarily closely approximate it with a neural network, which will have a single hidden layer with nonlinearity, and then it's going to be a, a linear combination. So we have the linear combination here. This sigma is a nonlinearity. It has to be a non-polynomial function. And this AI is just classical affine transformation. So he showed in 93 that if someone gave him a continuous function, he can approximate it arbitrarily closely. I think that's kind of known concept. And I wanted to know if the solution that I was talking about has some kind of similar properties as the normal neural network. Right? So if they are universal approximator. So just to give you an intuition, maybe for those of you who are younger age, the proof of the theorem is quite simple for the continuous functions. It relies on Stone-Weierstrass theorem, and the Stone-Weierstrass theorem said that if you have a set of functions, that's this algebra of the functions defined on a compact set, if this set of functions satisfies two properties, that means that the first one, it separates points. So if there are, let's say, 2 points that are different from this compact set, there is a function f which can, which have the different value on those points. So that's the separation. And if for each point on that compact set there is a function which is non-zero, then this set of functions is dense in this continuous set of functions, right? So in order to prove this this theorem about universal approximation on Euclidean spaces, you just need to verify these two to let's say preconditions, and then just by using Stone-Weierstrass theorem, you are done. So that's fantastic. By the way, the Leshno's paper goes then into a complication of extending, this proof to measurable functions. So he tries to show that you can approximate measurable functions. But this first part is relatively simple and easy to understand. So let's now move to the subject of let's say my issue, and that was the set, right? So as I told you that in the structured formats you have arrays. Those arrays can have arbitrary number of items. And you would kind of like to know have something like a universal approximation theorem on the sets. So I was looking how people deal with that, and there was a, let's say, line of research who has defined the let's say the kernels on sets, and they say that the set is just a it's just a realization of a random variable defined on this input space. So they would say that each array that you observe is defined by some probability distribution, and when you see two arrays, let's say from different classes, they come from two different classes of probability distributions. So the model assumes that if you are sampling this array, you first sample a probability distribution, and from that probability distribution, you start to sample these items in the array. So even within the same class, each array, so the items in the array can be generated by different probability distributions, and your goal is to, let's say, classify classes of probability distributions. Am I clear, or should I repeat this?
Is it any probability distribution is okay? Compact, it has to be compact or not? Compact is.
Oh yeah. So of course, so it has to be defined on a compact set.
Okay.
And the set of probability distribution has to be compact.
Okay.
But it's quite general. Okay, so what we did, we decided that we will extend the universal approximation to these sets. So we assume that we have some probability. We have a compact set of probability measures on a metric space, and we have some functions which project these probability measures to real numbers, and we want to let's say, arbitrarily closely approximate these functions from which projects the probability distribution to the real number. And the proof and the idea kind of mimics the proof of Leshno. So we again assume that there is this linear combination of some nonlinear functions, but these FIs, so originally in Leshno, his FIs, which are denoted here AIs, were just affine transformations. In our case, these FIs are integrals over the input space. So we assume that the probability are defined on a compact space X, and our projection to the real number would be an integral of some function defined on X to real number, and this integral takes this probability distribution and converts it to real number. And then you just do the regular neural network. And if you think about this integral here can be replaced in finite, in a finite sample setting is replaced by mean. So when on the beginning I was talking about that I'm taking element-wise mean or element-wise maximum, I will talk about maximum a little bit later. That element-wise mean is important for the theory. The element-wise mean is a finite sample estimate of this integral. Right. Does it make sense?
Yes, good.
Good. The proof is essentially just for the proof you need to just verify again the preconditions of the Stone-Weierstrass theorem. The second part is simple, like the non-vanishing, and the separability is based on this lemma. It's really a lemma. That lemma was published in this textbook, Real Analysis and Probability, and I discovered this lemma when I was doing my PhD, and I learned about things called Hilbert-Schmidt independence criteria and maximum mean discrepancy, like done by Arthur Gretton mainly. I learned about this lemma, and that lemma says that if I have two probability measures, P and Q, defined on some compact set, they are different. So sorry about that. Okay. Then there exists a continuous function which for which the integral is different. And if you think about this lemma just is essentially that part that you need for preconditioning for the preconditions of the Stone-Weierstrass theorem, and you just need to deal with kind of boring stuff like to make everything, to approximate it by more closely than epsilon half, such that when you like some two approximations you are like reasonably close, but that's a mechanism. But the proof is just based on this lemma and it by itself. And then we need to deal with these key value sets. So this is almost the same as the universal approximation theorem of the of Leshno, but you need to extend that to metric compact spaces because we need to be able to deal with cases when this item here is actually string is not just a string, but it can be an array. And in let's say our theory, that array is a probability measure, so it's no longer Euclidean, and you can no longer use the Leshno's proof. So we have kind of a technical theorem which just extend this to compact metric spaces, but the proof is essentially like the Leshno. And so with like these three tools, we have like an encompassing theorem which tells us like if that which defines a class of spaces which contains all compact subset of Rn. Okay, that's the Leshno thing. It's closed under finite Cartesian product, so that's the last theorem. And if there is a compact set, or if there is a compact set in this class of spaces, like any compact set of probability distributions on this subset is in this subset. So it's sort of a recursion definition of JSONs or of these hierarchical functions, hierarchical data, and then we just know that our scheme. Using our scheme, we can arbitrarily closely approximate any continuous function. So, and we did it just to know that our solution is correct. Like so, just like when people take the super vector machines, they know that they can arbitrarily closely get to optimal Bayesian classifier in infinity. When they took neural network for Euclidean spaces, they know that they can arbitrarily closely approximate it. And we know the same. So we kind of know that the solution is correct. Yeah, so in the third part, I was talking about explanation. So again, like being in the industry, I think that explanation is quite important. So you got the sample from the beginning, and you train a model, and it tells you it's IP phone. And you will say, like, why? Why do you think this is an IP phone? And the people likes to know why. Right? So the solution to this is simple, relatively. And the nice thing is that the explanation I would call it speaks your language. Since you do not really derive new features, you take the sample as it is stored in your database, the explanation is along the same lines. So as I told you, like the important thing or property of our solution is that you can remove any part of the sample and the classifier can still deal with it. So if I remove, like two parts, two items from the services and like device ID and IP, the model still tells me it's an IP phone. Like if I remove device ID, IP, and MAC, it tells me it's IP phone, but the probability is quite low. So there is this concept of Shapley values. It's a concept from, let's say, cooperative game theory, which tells you that you can roughly estimate the importance of each feature. In our case, the feature is an item of a given sample. So that's why you can see that I have three services here, 3 times services, because I have three times the service array has 3 items. If it would have less, it would have less these. And you start to sample the subsets of the sample, and why it doesn't work? And you just calculate for each item if it was present. Let's say you calculate the average value, average output of the model when the feature was present and when it was absent, and you take the difference. So if I go a little bit deeper, you start to sample, you go like this, and then we turn the automatic scrolling, and you can see that the Banzhaf values kind of tells you which feature seems to be important and which seems to be not important, but we do not end up here. Because if we have this, let's say, ranking of importance, we can really start to prune the sample. So we can really start to remove the things from the sample and just questioning, like, what's really the minimal part that you need for a correct classification. So if I do this for this particular example that I have here, you will end up with this. The MAC address is the only part from the whole sample that is sufficient for a correct classification that it's an IP phone. And because I am in Avast, I asked people around, like, why is that? And they told me, well, it's easy. Because in these three digits in the MAC address, there is a vendor. So I put it, MAC address lookup, and it tells me, yes, these devices are created by this company. And what that company does, it's making IP phones. Right? So the explanation sort of works quite nicely. You can remove it and you can start to repeat the process for another explanation, but you can see that at this moment, the classification is quite weak. the confidence is quite low, so I wouldn't say that the classification in this case, I think would be more like a fraction of it would correspond to, let's say, the frequency of IP phones with this type of features in the data set. So I wouldn't call it very convincing. And that's it. So if you would like to play, we created 2 libraries, which if you want, I can show you a little demo that I made. This first library just implements the bolts and nuts. So it implements this whole necessity to deal with these structures. And this JSON grinder just makes the classification of JSONs very easy. So if you give me 1 more minute, I can show you an example. So for this device ID, well, if I load the data, I create something which I call schema. It's done automatically. I have my JSONs in these training samples, and it tells me it discovers the structure and it discovers the types of the leaves. And as I said, creating conversions for leaves to let's say vectorial representation is quite trivial. So we take that and create an extractor, and the extractor takes the JSON and projects it into a, let's say, structure which facilitates the, let's say, efficient training. And by facilitating, what I mean is that it takes the, let's say, samples and joins them in the structure such that when you have leaves of the same times, it's a continuous array, such that you can use matrix multiplication and the sorts of the stuff. And then the function creates automatically or semi-automatically according to your wish the model, which reflects the structure, and you can train the model. Right? And then on the motivation, I was telling you that here we have been using these default theory, sorry for this. So when I was telling you that we compared, we created this comparison, the default was really that we just followed these steps. So in the library, there is a kind of example script, and we took that example script and we just run it on the data, on these complicated JSONs, and we achieve this accuracy. And when we have been tuning, we got better, right? So I actually still consider that quite cool, and especially I like the explanation part. That's what I am kind of interested at the moment the most, right? So yeah, so these 2 names, this is my colleagues, and they did a lot of engineering work on these libraries because I'm kind of messy programmer and they are the proper programmers. So they did these unit tests and everything. So if you want, you can try it on the data of your wish and let me know if it works. And that's it.
Okay, yeah, thank you very much, Dr. Pevny. And is there any other questions from the audience?
Hi, this is Leo. We actually emailed each other talking about the discussion, and I do have some questions. Actually, I have 3 questions, but the first 2 maybe kind of related. The first is about how you project this this feature to the vector. I mean, I think this should be kind of fundamental things in computer science, but I'm not familiar with that. So the question is, for example, how can you project the port and MAC address to
okay, yeah, so as I said, projecting you take a one-hot encoding, right? So you know that if this is, let's say I have it here, let me go back. like it should be here, right? Like if this is TCP, let's say the first item would be 1 and the second would be 0. If it's gonna be UDP, the first one would be 0 and the second one would be 1. And then in these arrows, there would be a neural network, like the classical feed-forward neural network that you know, which will go from dimension 2 to dimension of your choice.
Oh, okay. And okay, this make okay. I think I got my answer. But so and then if, for example, in some of the data, the MAC address is missed, then it just
so for that, as I said, like for the MAC addresses, you can use. There are various ways how to convert strings to let's say array of finite dimension, like the vector. But what I have implemented into the library, and it stays there, it's an engram, right? So in engrams, or trigrams, let's say specifically, you take, let's say, if I take this MAC address, it would be like AC double column, and you treat it as a vector of dimension 3, and you calculate a special number. It would correspond to a number because you can imagine that it's going to be a, let's say, a number in it's gonna be in a field which would have like 250, or you can think about it as a vector in a Euclidean space, which would have like 256, and 256 discrete dimensions.
Okay, makes sense.
And you do this for like all trigrams and take the sum. So this is like, pretty classic. So I was not really interested in that part.
Yeah, I know. I'm also not interested. But my question is, what if, for example, some of them is just missed in this data set? So you just put
okay.
Right?
So you are asking like if there is something missing.
Yeah. For example, ID or MAC is missing, right?
So I can tell you the evolution. So originally, when something was missing, we just put 0 there, right?
Okay.
And then I was thinking always like, why 0? Right?
Yeah, why 0? That's also my question.
Yeah,
why 0?
Why not 1? Or why not -1?
Yeah.
So then we decided that we will. So let's say that this MAC address would be represented by a vector of dimension 10, like just for an example, right?
Okay.
We will have another vector of the same dimension of 10. And when that MAC address would be missing, we would put that vector, we would essentially put a special vector, but that special vector would be part of the parameters that you are optimizing.
Oh, you put it this way. Okay.
So, like, if the MAC address would be filled, I would just fill it with, like a value it corresponds to. If the MAC address is missing, I would replace it with a special vector with some values, but those values are free parameters that I'm optimizing during training.
Okay, I saw you like put random vectors. That is like, for example, just comes from another device, but now you are trying to optimize that. I think it is more reasonable. Yeah, I think.
So think about it that most of the people would put zeros, and I let the neural network to choose her values during training. And we do the same stuff with the array. Like, so if you have services and that you would encounter, and these services would be empty, like we would have special vector which would represent an empty service, and that special vector is again parts of the of the parameters that you are optimizing during training.
Okay. I got a point. I think it makes sense. And the second question is about the you know, in the output there's like some probability. I know you would I suppose you did that with the softmax. And I'm just kind of curious. Did you like I mean, I was fascinated by the result that, for example, if you don't have the MAC address, then your result is basically pretty uncertain. And that is, I think that okay, that is very good result. And I was wondering, like, is this just like the results you got, or you design some mechanism?
No. This is like really like. Unfortunately, I cannot share the data set with you. Right? If you read the Kaggle challenge, the data set was taken down for let's say privacy, right? But okay, it's really something that I just like took out of the box. Like, it's not like, of course I have like tried to find something funny or interesting, like from the, but it wouldn't something that, you know, I would specifically pick. So I had like my my favorite examples was that I was detecting audio devices because they have been connecting to Spotify. Like,
okay.
And it makes sense.
Yeah, and okay, and actually the reason why I asked this question is okay, it's basically about the uncertainty. So this is thing in my mind. I'm kind of concerning the gap between finite a set of consists of finite elements and a probability distribution. I mean, they're kind of different. For example, if this set consists of like three different elements, and then, you know, you take the average for f, and then you put this stuff to another neural network. This result gonna be identical to the one that, for example, you only have one element, but this one element is like
yeah.
you know
Yeah,
what I mean?
So this is absolutely true. Let's say when I was proving the theory, I was looking how people deal with these let's say sets, and I came to this definition because that's how people dealt with it in
point cloud, right?
No. So I went even, you know, like, so I was looking into kernel machines.
Kernel machine. Okay.
Because there was a line of work by Ingo Steinwart, and he was showing how to define kernels on spaces of probability measures. And then Bernard Cholkov used that to define kernels on sets. So I took that representation from that. You are right that you can get into this kind of ambiguity. And like in practice, and I think the default in the library is that I always use mean and maximum.
Okay, mean and maximum.
Okay, so let me just show you. So here, when I'm aggregating, right, I always use mean and maximum, and it has a very clear sense. Like, you know, like when Andrew was introducing me, like my background was in security, and in security, people make typically devastating mistakes. Like for example, like the author would write a malware and he would put a unique string. Like, there would be a unique string. That means that you do not need to bother with modeling probability distribution. You just need to detect that single string, right? And to detect these things, the maximum is the thing to do, right? Because it's either not there, and the maximum is going to be, you know, let's say around 0, or that individual token is there, and the maximum will shoot.
Okay.
Like, again, like there is a theory that you know, if you have a KL divergence between two probability measures, and that KL divergence, those two probability measures, let's say, are not defined on the same support, they would be slightly misaligned.
Yeah.
Right? The KL divergence is infinity because there is a division of 0.
Yeah.
And detection theory tells you if it is infinity, you can create an arbitrarily precise detector because you know that when something falls outside the support of the other distribution, you know that it has to be that one. It can't be that the other one. And that's why I'm saying that in practice, especially in security, the maximum is very good because you are not essentially comparing probability distributions.
Okay.
You are checking for special tokens because the malware authors are making devastating mistakes. Like the distribution is not equal.
Okay, yeah, it makes sense. Yeah.
And so that library, like my student, and one of the authors, he was playing a lot with these aggregation functions. So he had aggregation functions which had parameters, so they can optimize. They can optimize. They can, for example, smoothly go between like mean and maximum. And he was showing in his diploma thesis the advantages. But in practice, like mean and maximum together work really well.
Okay, mean and maximum together. Okay, I got it. Thank you. Yeah.
Hi.
I think that's all my question. Yeah.
Hello, can I have a question?
Sure.
I'm Ting Wei from Brown. So, by the way, I'm the another author of the paper that
I was discussing.
yeah. So when I thought about this neural network architecture, I'm thinking about a subset of Euclidean space. But here, I think the interesting thing is you're thinking about the tree, right? The tree structure. I'm just curious, have you thought about some other data structure like graph or even a neural network is a structure?
Okay, so I wasn't, the graph is essentially solved. You would use graph neural networks, which in my view is kind of implementing message passing algorithm that you know from loopy belief propagation. Right? So I wasn't really interested in like graphs, although lately I was playing with that, and again, I made this, let's say, design choice that I would take a graph, and I will ultimately project the graph into a vertex, not vertex, into a vector. So that would so that I can have a recursion. So ideally, for me, the graph is something that I use to describe, let's say, nature of phenomena. And I always think about graphs with vertices having rich description by these trees, and edges having rich description by these by these trees. And then on top of that, you can use the normal graph neural networks. But so what I would need to say, so in my implementation that I have, I allow the recursion. So you can have the graph, which will have vertices described by graph and edges described by graph and so on because of the recursive principle. But I wasn't thinking really to go into different types of data, probably because I don't have access to the. Moreover, I don't consider this thing to be, let's say, finished, right? Because I, let's say, know very well how to do discriminative learning. Right? That's trivial. But for example, I'm still not clear how to properly define likelihood on these spaces. Just a simple concept, really, likelihood is super simple. We do maximum likelihood estimates all the time. I don't really know how to do that. I don't know how to generate these things. So the space is full of like generative adversarial networks and variational encoders and whatever. I don't know how to generate it, like, let's say, correctly. As I said, like, I would like to have a theoretically correct solution, not a solution. Like, I would like to have something that, and the reason why I think this is important is that, let's say, a lot of data that we are getting are without labels. Like, if you think about like analyzing malware, malware is described usually by these structures. But if you want to analyze malware, you need to ask a guy who really understands the stuff to analyze it. I would like to simplify his job. And I think that unsupervised learning would be an interesting, but I don't know how to do it. So that's sort of like why I didn't divert to other type of data.
I didn't have an idea in mind, but I'm just curious. Maybe this kind of structure can be used to search the architecture of the neural networks. I don't know.
I'm not sure, because like the stuff that I have been talking about is purely discriminative. Like, you need labels.
Yeah, I see. Yeah. I think, Liu, in our paper, we had some. Do we have some unsupervised learning? I think.
No, we don't. We actually not.
Well, you do, because you are training GANs, which I would call as a thing. But the tricky part here is that you need to sample set. And to sample sets, you need to take a gradient of discrete distribution with respect to its parameters, which is quite tricky. And moreover, imagine that you would, like, sample these services, and from that you need to, let's say, sample these items, and you need to align them. So, like, I wish that I will get to that, but it's sort of still slipping.
Okay, thank you.
Yeah, thank you.
Thomas, I have a question for the library. For the library, because the library that you show, what you show as the code was only for this data, but I'm interested to use this for my biomedical data. How is this to swap the data?
Well, it's quite easy, but it's written in Julia language, right? So if you would let me, so I will get from this, like, I will just show you. So if I go to this JSON grinder, there is in examples notebooks. So if you start with this example, frequently you need to change the source of the data such that you load it. And if your data contains keys like labels, you just need to like put the labels. And I see that guys even simplify it, that it's loaded from the some like metadata. So like to achieve what I have been showing you in the demo with this device ID stuff, it's really this simple script. Okay. The trouble might be the Julia language. But besides that, it's very easy.
Yeah. So could we work with one of your students? Maybe he can help us, or she?
Sure. If it is after NIP's deadline, I can ask,
Yes, yes, after May 28th, yeah.
yeah, after a NIPS deadline, I can ask like one of my PhD students to help you with those data.
Okay. Yishan, are you still here or you sign off? Yishan is working with this data set. But, okay. Yeah. Okay, that's great. Thank you very much, Thomas, for taking the time today.
No, it was like, I'm really happy that you invite me. Like it's always fun, and like we can really help you. Like basically, like I am, by the way, like really interested like this type of data. And one thing that I'm really interested to find a data set when this approach would fail.
Well, let's say that we have this accord. I mean, we have several databases, but like for example, the missing data, the way that doctors would do it now, they would say, okay, use, because in time, right? Use the same data as before, let's say, from the previous visit. Yeah, for your blood pressure, let's say, if you're missing it, yeah, so which is not satisfactory, let's say, because obviously you're aging and you are getting worse, not better, or different. But unpredictable. It's not, you're not the same. So it's so that's how they fill up the missing data. But yeah, we'll send you email when you finish your NeurIPS papers.
Sure, I will.
Okay. And Rui, I think maybe you can finish here.
Yeah, okay. Yeah, thank you very much again, Dr. Pevny, for your great presentation today and your time.
Thank you very much for having me.
Yeah, no problem.
So I stop sharing.
Okay. Yeah. So far is the Crunch seminar this week. And yeah, hope that everyone will have a good weekend and see you next week. Yeah. Bye-bye.
Thank you, Rui.
Thank you very much. Bye.
Bye.